In any programming language, it's important to be able to collect together values and refer to them by a single name. In Haskell, these are done using lists. Now, in other programming languages that you may know, like C, C++, or Java, the usual data structure for collecting a bunch of values together is an array. So you might have come across lists before, but in Haskell it is fundamental that the basic collective type is a list. So a list is a sequence of values, and more importantly, it's a sequence of values of a uniform type. Lists are denoted using this square bracket and comma notation. So the square brackets denote the beginning and the end of the list, and the values are separated by commas. So the list 1, 2, 3, 1 is a list of integers, so it's a list of type int. True, false, true could be a list of values of type bool, and so on. So the crucial thing is that the underlying elements must have a uniform type. So we cannot write, for example, a list with mixed types like 1, 2, true, or 3 and a. Okay, so if you are familiar with a language like Python, okay, Python does allow this kind of mixed thing and calls it a list. So these are not the same as Python lists. Okay, in a Python list, the values need not be of a uniform type. In a Haskell list, they must be of a uniform type. So since the underlying elements are of a uniform type, we can assign a type to the list itself. So if the list of values has type t, then the list itself has type square bracket of t. Right? So now since here inside we have ints in the first list, we say that the type of the list is square bracket int. Similarly, since these are bool, the type of this list is square bracket bool. The notation for an empty list is just an opening bracket followed by a close bracket. Now, technically, there is an empty list of type list of int, there is an empty list of type list of bool, and so on. But we will uniformly use the same notation without specifying what type it is. So for every type of list, the empty list is given by the same symbol. So this as a type should be read as list of int. Okay, so if you want to read it out, what is the type of this value? This value has type list of int. So of course lists can be nested. So we can have lists of lists, but again each of the internal lists must have a uniform type. So here now we see that each of these is itself a list of int. Here this is the famous empty list, which could be denoting any type, but by context it is a list of int. Again this is a list of int. So we have three lists of int themselves enclosed in a list. So this overall thing is list of int, right? So this is my underlying t and my outer bracket, right? So my underlying value type is list of int, and now I have a list of those. So lists are built up in a very specific way in Haskell. Lists are built up by adding elements at the front, and this operator is denoted by colon. So if I have a list, right, and if I want to put an element in front of it, then I can put the colon and have the value in front. Right? So 1 colon 2 3 gives me the list 1 2 3. So what we will be doing in these notes, we will try to do at least, is use this symbol to denote the fact that this value returns this value. Okay, so it's not like an equality, but this expression is equivalent to this expression. So Haskell actually builds up lists in a standard way using this operator. So we always start with the empty list and then keep adding elements in front of it. So when we write the list 1 2 3, it actually means that it was built in reverse by first appending 3 to the empty list, then appending 2 to the 3, then appending 1 to 3. Right? So the list 1, 2, 3 that we write for legibility is actually, in terms of this fundamental colon operator, is actually 1 colon, then 2 colon, then 3 colon, empty. So this is the initial step, then this is the next step, and this is the final step. Now of course it is always tedious to write all these brackets. And so similarly to types, so if you remember we said that if I write int star int, it's actually bracketed from the right. Okay, so we have implicitly that this is the bracketing. So this is what is called a right associative operator. We associate from the right. So similarly colon is a right associative operator. So if I just write the colons without brackets, it means I bracket from the right. So I can write 1 2 3 empty as 1 colon 2 colon 3 colon empty list without writing the brackets, and it will mean the correct thing. Now it's important to note that these are all just different ways of writing the same thing. Okay? So if I write 1 colon and the list 2 comma 3, or if I write 1 colon 2 colon 3 comma the colon the empty list, all of these are actually the same value. So if I try to ask the interpreter whether this is equal to that, so this, remember, is our equality check, then it will return true. Similarly, if I say 1 colon 2 colon and the list 3, this will be equal to 1 comma 2 comma 3 and so on. Okay? So whenever we write these, we should remember that the way we write it doesn't change the fact that all of these forms are internally this form. Right? So internally, the only form that matters is there of the form 1 colon 2 colon 3 colon empty list. Right? How we write it is flexible. So when we have a list now, we therefore have in some sense the first value, right? And then we have the rest of the values attached by a colon. So it's conventional, if we use the term x for the first value, to use x's. So this is an x followed by a bunch of x's. Okay, that's how you're supposed to read it. So now what we have is this operator that puts them together. So we have functions that take them apart. So this is called the head of the list, and this is called the tail of the list. Right? So the head of the list is a value, and the tail of the list is another list. In particular, if I take tail of a list with one value, okay, this is the same as 3 colon empty. So here the tail will be the empty list. Okay? So we can only do head and tail on lists which have at least one value, because otherwise I can't split it. I can't split the empty list. So both head and tail are defined on non-empty lists. Head returns a value, tail returns a list. So now we would of course like to define functions that operate on lists. So it turns out that induction is a good way to define functions on lists. So recall how we did inductions for numeric functions, especially for functions on whole numbers. So we said that we would define a base case for the value 0, and then for a value n plus 1, we would define f in terms of the value n plus 1 itself and the value of the function f on a smaller value f of n. So for example, we said that n plus 1 factorial is n plus 1, the value n plus 1 multiplied by n factorial. So this is the value of the function. So this is f of n. Right? So this is how we did inductive definitions on numbers. So what is the natural notion of induction for a list? Well, it turns out that for a list, the natural notion of induction is the structure of the list, or you can think of it in terms of the length of the list. Okay? So the base case is the list we start with, which is the empty list, and then we add one element at a time. So if we have a non-empty list, we can strip off the outermost colon and define a function in terms of the value that we get, the head, and the value that we have inductively computed on the tail. So let's look at an example. So supposing we want to compute the length of a list. Right? So it is very clear that the length of an empty list is 0, and the length of any list with more than one element is one more than the list length of its tail. Okay? So here is a function which we'll call myLength, because there is a built-in function length and we don't want to confuse the Haskell interpreter if we actually try this out. So myLength takes a list of integers and returns an integer which is the length of that list. So the base case, as we did for, so if you remember, we used to write factorial of 0 is equal to 1 and factorial of n is equal to something. So again, we have two cases. We have myLength on the empty list, which is 0. And now if it is not the empty list, then it will not match this pattern. So this is like a pattern now, right? So if I give an argument which is not the empty list, it will not match this definition. It will go to the next definition. So now I'm guaranteed that the list is not empty. If the list is not empty, it has a head and it has a tail. So I can say that the answer is 1 plus inductively the length of the tail. Right? So this is a typical inductive definition of a function operating on a list. Now it turns out that we can use pattern matching because of the unique way in which lists are built up. So we don't have to actually explicitly call head or tail when we write inductive definitions. Every non-empty list can be uniquely decomposed as its head and its tail, and this can be represented as an expression of the form x colon x's. So the first variable refers to the head, the second variable refers to the tail. So we can write the same function as follows instead of writing tail in the second definition. So earlier we had written my length of L is 1 plus my length tail of N. This was our earlier definition. So now we say, well, let us directly break up our L, which is not empty, into the head and the tail, and just use the variable that matches the tail as the recursive call. Now notice this bracketing. Okay, so we had the same problem at the beginning when we wrote in our first week. We said that we must write this because if we write factorial of n minus 1 without brackets, then Haskell will try to bracket it this way because function application has a tighter binding. It has precedence over arithmetic. So similarly here, function binding will have precedence over this. So it will try to say that this is my length. If I write my length of x colon s without this, it will try to say it is my length of x colon xs, and then it will probably give a type mismatch. So we have to put these brackets when we use a list pattern for a non-empty list. So just to get some practice, let's look at another function which is inductively defined. Supposing now we want to take a list of integers and add them up. Right? So we want to sum up the values in a list. So again, the sum of the empty list is just 0 because there are no values. And now if I want to sum up a non-empty list, I inductively sum up the tail and I add the head to it. So it is x plus the sum of the tail. So it's easy enough, right? My sum of the empty list is 0. My sum of x colon x's is x plus my sum of x's. So this is a general pattern. So you write inductive definitions by defining the value for a non-empty list in terms of the head and the value of the function on the tail. Okay, so we will see more examples in a subsequent lecture this week of more interesting questions than just length and sum. We will see several examples to get familiar with this concept. So a list is a sequence, right? So we have implicitly values in it which are numbered with respect to 0. So if I have a list with n values, I should think of that list as consisting of x0, x1 up to xn minus 1. Right? So we have position 0 to n minus 1. This is quite traditional. So arrays in languages like C, C++, Java start with 0, lists in Python start with 0, and so on. So the positions are 0 to n minus 1. So Haskell gives us a value, gives us an expression which looks like an array access with a square bracket to access the jth position. So the jth position, remember, will be the j plus 1th value because the positions start from 0. So if this is position j, then Lj will give me the value at that position. Now one important thing to remember is that actually this is only a short form for the following expression, which is x1 colon x2 colon and so on, and then xj colon xj plus 1 colon and so on, and then finally xn minus 1 colon empty list. So this is what the list really looks like. So in order to get to the jth value, I have to extract the first this colon, then I have to extract this colon. So I have to peel off each thing until I reach this value. So it takes me j steps to actually get through. So this should be, sorry, x0, x1. So to get from x0, x1 to xj, it takes me j steps. Right? So therefore, accessing a value in a list is not a constant time operation, unlike an array. If you have an array in memory, then you can compute the position of any value in the array by looking at the offset, because these are all defined to be contiguous values of a uniform size. In a list, we only know that it was attached. So we have to detach the preceding elements to get to the internal element. So it's not a random access device. Right? So it takes time proportional to the position in order to get to an internal value inside a list. So this is important when we start looking at functions and trying to determine their efficiency and complexity. So some functions which work well on arrays, which can access a, j in unit time, will not work so well on Haskell lists. So Haskell has some nice notation to denote sequences of values. So if we want a range of values, okay, a range of values from m to n, we just write m colon colon n. This means the list m, m plus 1, m plus 2 and so on up to n. Of course, now if the upper limit is smaller than the lower limit, then this will not give us a list. Right? So if I say 1 colon colon 7, I get 1, 2, 3, 4, 5, 6, 7. Notice that the last value is included. Some of you, if you know Python, will see that in Python, if I write range 0 n, then I will get the list that goes from 0 to n minus 1. Okay? So in Haskell, it is not like that. In Haskell, the upper limit is included in the final list. So if I say 1 to 7, I get 1 and I get 7. So if I say m and I use the same upper limit as the lower limit, then the value of the list 3 colon colon 3 dot dot 3 is 3. And if I use an upper limit which is smaller than the lower limit, then I will get an empty list, because starting from 5 I cannot go up. So the idea is that you start from the lower thing and keep adding 1 so long as you don't cross the right. Once you cross the right, so once I go to 8, I stop and I throw it away. So therefore if I say 5 dot dot 4, I get the empty list. Now sometimes we would like to get not every value but values by skipping a fixed amount, what we would call an arithmetic progression. So we want a plus d, a plus 2d and so on. Okay? And now of course when I say a plus d, a plus 2d, there is no guarantee that the number I choose on the upper bound is actually part of the progression. So here if I do, the way we do it in Haskell is we give the difference by example. So we give the first value and then we give the second value. So implicitly this says that d is equal to 3 minus 1 is equal to 2. So it says I must be skipping 2. So 1, 3, 5, 7. Then the next value generated would be 9. But 9 would cross this upper limit of 8 and so we stop at 7. Similarly, if I say 2, 5, then here it says that d is equal to 3. And so I have 2, 5, 8, 11, 14, 17. The next value would be 20. But 20 goes beyond 19. So we have to stop. So we said that if we do something like 5 dot dot 4, we'll get an empty list. But it is often useful to be able to count backwards and not forwards. So we can use this idea of an arithmetic progression to count backwards by giving the second value smaller than the first value. So if I just said 8 colon dot dot 5, okay, this would give me the empty list because it would implicitly try to add 1. But if I say 8 comma 7 dot dot 5, then I fix d to be equal to minus 1. So now it will start counting down. It will go 8, 7, 6, 5. And the idea is of crossing. Right? It's not greater than or less than. If I cross the right hand side limit, then I stop. So when I go to 4, I have crossed that limit, so I stop. Likewise here, the difference is minus 4. So if I keep going down, after minus 8, the next one would be minus 12. So I would have crossed minus 9, so I stop. Right? So it's quite intuitive and it's very clear how to specify ranges in Haskell. So to summarize, a list is a collective set of values of a uniform type. So it's a sequence with positions 0 to n minus 1. And because they are of a uniform type, a list of values of type t has type list of t denoted by square brackets around the t. So lists are internally represented in a canonical way. All lists are built up from the empty list using this append to the left operator, which adds one element to the left each time, which is denoted by colon. The name of the operator is colon. Okay? And because we have this canonical way in which lists are built up, we can decompose lists using the same operator and define functions by structural induction. We can define functions as a base case on the empty list and then define it on lists of the form x colon x's. And we can use this pattern x colon x's in function definitions to easily define such inductive functions. And the last thing to remember is that because of the way that lists are represented and implemented, these are not random access lists. Okay? These are not like arrays in C, C++, Java. It does take time proportionate to the position to reach an internal position in a list.